In our digital lives, we're stuck in this constant dilemma, right? We have to prove things all the time, who we are, that we're old enough, that we have enough money. But to do that, we usually have to hand over sensitive, private data. It's this fundamental tug of war between proving something and protecting ourselves. But what if there's another way? What if you could prove you know a secret without ever revealing the secret itself? Well, that's not magic, it's cryptography. And today, we're diving into the incredible world of zero-knowledge proofs. All right, so here's our game plan for this explainer. First, we'll get our heads around the basic idea, proving without revealing. Then we'll look at the 3 core properties that make these proofs tick. After that, we'll explore the whole zoo of different ZKP technologies out there. And finally, we'll see how this stuff is moving from pure theory into the real world. Let's get into it. All right, section 1, proving without revealing. We're going to start with the core idea behind zero knowledge, this central puzzle that ZKPs were invented to solve. It feels a little counterintuitive at first, but trust me, it's the key to so much. So this is really the fundamental question, isn't it? How can you prove you know a secret without actually, revealing it? I mean, think about your daily life online. Every time you log in, you give up your password. To prove your age, you show your entire driver's license, name, address, date of birth, everything. It's an all-or-nothing game. ZKPs are here to change those rules completely. Okay, so what is a zero-knowledge proof, or ZKP? At its core, it's a type of conversation, a cryptographic protocol between 2 parties. You have the prover, that's the one with the secret, and the verifier, the one who needs convincing. The prover's goal is to convince the verifier that a statement is true, but without giving away any extra information. It's the difference between showing someone your password versus giving them a mathematically solid guarantee that you know the password. The verifier walks away 100% convinced, but they learn literally 0 about the secret itself, hence the name. I know, this probably sounds a little abstract, maybe even a bit like magic. So to really build our intuition here, we're going to use the most famous analogy in the ZKP world, the story of the Alibaba cave. It's a brilliant way to understand the concept without getting bogged down in the heavy math, at least not yet. Okay, picture this, a cave shaped like a circle with 2 paths, path A and path B. At the very back, there's a magic door that connects the 2 paths, but it only opens with a secret password. So we have Peggy, who is our prover. She claims she knows the secret password. And we have Victor, the verifier, who's not so sure. Here's how it works. First, Peggy goes into the cave and randomly chooses either path A or path B. Victor waits outside and has no idea which path she took. Then, Victor walks to the entrance and randomly yells out a challenge. Hey, Peggy, come out of path B. Now here's the crucial part. If Peggy really knows the password, this is no problem. If she's already in path B, she just walks out. If she's in path A, she just whispers the password, opens the magic door, crosses over, and comes out of path B. She can always meet his challenge.
But what if Peggy's bluffing? What if she doesn't know the password? Well, now she's in trouble. She's stuck in whichever path she first chose. When Victor yells out his challenge, she's got a 50-50 shot of being in the right place by sheer luck. Okay, maybe she gets lucky once, but what happens if they do this again and again? If they repeat this little game just 20 times, the chances of her guessing correctly every single time are less than 1 in a million. At that point, Victor can be statistically certain she isn't just lucky. She must know the secret. And here's the kicker. Throughout this entire process, Victor has not learned a single thing about what the password actually is. Nothing.
Okay, section 2, the 3 core properties. The Alibaba cave story gives us the intuition, but for a protocol to be a real zero-knowledge proof, it has to follow 3 very strict rules. Think of these as the pillars that hold the whole thing up, making it both trustworthy and secure. The first property is called completeness, and it's pretty straightforward. It just means that if the statement is true, if Peggy really does know the password, then she will always be able to convince Victor. An honest prover can always pass the test. The system works when everyone's playing fair. Next up, we have soundness. This is the flip side, and it's your security guarantee. Soundness means that if the statement is false, if Peggy is lying and doesn't know the password, she can't fool Victor. Sure, she might get lucky once, but the protocol is designed so that the chance of a liar fooling the system becomes vanishingly small with repetition. Eventually, a dishonest prover will get caught. You can't cheat a sound system. And property number 3 is the most important one, the one that gives ZKPs their name, zero knowledge. This is the privacy guarantee. It means the verifier learns nothing, and I mean nothing, beyond the simple fact that the prover's statement is true. Victor is now totally convinced Peggy knows the password, but he has no more information about what the password is than he did before they started. The only thing transferred was a single bit of information. Yes or no, true or false. So now we've got the core principles down. But how does this theory actually translate into technology that we can use? Well, welcome to the ZKP technology zoo. It's not just one thing called a ZKP. It's a whole ecosystem of different approaches, each with its own unique characteristics, its own pros and cons. The first big split in the zoo is between interactive and non-interactive proofs. Our Alibaba cave example? That's interactive. It needs that back and forth challenge and response between Peggy and Victor. That's fine for a story, but it's not practical for most real-world applications. The real game changer was the development of non-interactive ZKPs, often called NISQs. With these, the prover can just generate a single, self-contained proof. It's a little bundle of data that anyone, anywhere can check at any time, without having to talk to the prover at all. This was the breakthrough that made ZKPs usable for things like blockchains.
Okay, so let's look at the big three you'll hear about most often: zk-SNARKs, zk-STARKs, and bulletproofs. Think of this as a classic engineering trade-off. On one hand, you have zk-SNARKs. These are incredibly popular, and for good reason. The proofs they generate are super small, and they're really fast to verify. That's a huge deal for something like a blockchain where space and time are precious. But they come with a big asterisk. Most of them require what's called a trusted setup. We'll get to that in a sec. Then you have zk-STARKs. They don't need a trusted setup, which is great, and they're even resistant to attacks from future quantum computers. The trade-off? The proofs are much larger. And bulletproofs are another option that also avoids the trusted setup, with small proofs, but they take longer to verify. So you see, there's no silver bullet here. It's all about choosing the right technology for the problem you're trying to solve.
So I mentioned that trusted setup for SNARKs. What exactly is that? Well, before the system can be used, it needs a special one-time ceremony to create some public parameters. The problem is, the ceremony also generates a piece of secret data. And this data is so powerful that if someone got their hands on it, they could create fake proofs that look totally valid. They could basically print money or cheat the system without anyone knowing. This secret data is so risky, it's literally called toxic waste. The solution is pretty clever, though. They run these elaborate multi-party ceremonies where many different people contribute to creating the parameters. The security relies on the assumption that as long as just one of those participants is honest and destroys their piece of the toxic waste, the whole system is secure. All right, we've gone from the core idea to the different flavors of technology. Now for the most exciting part, from theory to reality. We're going to see how ZKPs are actually being used right now to solve huge real-world problems. This isn't just a cool concept in a research paper anymore. This is tech that's securing billions of dollars in value today. And the use cases are just exploding. We're seeing them make blockchains faster and cheaper with ZK-Rollups. They're enabling private financial transactions. They're completely rethinking digital identity. And they're opening the door to things like verifiable computation and even more secure supply chains. The list just keeps growing. Okay, probably the #1 application for ZKPs right now is scaling blockchains using something called ZK-Rollups. If you've ever used a popular network like Ethereum, you know it can sometimes get clogged up and fees can get really high. A ZK-Rollup is an ingenious solution. It takes a huge batch of transactions, we're talking thousands of them, off the main chain. It processes them all, and then it generates a single, tiny cryptographic proof that says, hey, I did all this computation correctly, and here's the final result. That one tiny proof is all that gets posted back to the main blockchain. It's a way to verify a massive amount of activity with a very small footprint, which drastically increases the network speed and makes it cheaper for everybody. And then there's digital identity, which is a huge one. Think about how we do this now. If a bouncer needs to know if you're over 21, you hand over your driver's license. They don't just see your age, they see your name, your home address, your exact birth date, your height, your weight, way more information than they have any right to know. ZKPs flip this on its head. In a ZKP-powered future, you'd just generate a proof that says, the statement I am over 21 is true according to my official digital ID. The bouncer's app verifies the proof, and that's it. They know you're old enough, but they learn absolutely nothing else about you. That's the power of what we call selective disclosure. And this really gets to the heart of why ZKPs are such a big deal. For decades, cryptography has been about protecting data at rest, encrypting your hard drive, or data in transit, like sending a secure message. But ZKPs, they let us secure data while it's being used. It's a paradigm shift towards securing the integrity of computation itself. For the first time, we can prove that a complex calculation was performed correctly, even on data that remains completely private. That is a massive leap forward. And it's amazing to think about how far this technology has come. It all started back in 1985 with a groundbreaking academic paper. For years, though, it was seen as just a theoretical curiosity, a really elegant piece of math, but way too slow and inefficient for any practical use. It really wasn't until the 2010s, with cryptographic breakthroughs and the launch of the privacy-focused cryptocurrency Zcash, that people saw it could actually work. And now, here in the 2020s, ZKPs are becoming an absolutely essential technology for scaling the world's biggest blockchains.
Now, we're not quite at the finish line yet. There are still big challenges to overcome. For one, generating these proofs can be incredibly resource-intensive, requiring a lot of computing power. And the expertise needed to build secure ZKP systems is still pretty rare. But the industry is moving fast to solve this, with companies developing specialized hardware, ASICs and FPGAs, just for speeding up proofs. And looking even further ahead, one of the most exciting frontiers is zero-knowledge machine learning, or ZKML. Imagine being able to prove that an AI model gave you a certain result without the owner of that AI ever having to reveal their secret proprietary model. The implications are staggering.
So, where does this all leave us? We've seen that zero-knowledge proofs represent a fundamental shift from a world focused on just securing data to a world where we can secure computation itself. They promise a future where we don't have to choose between verification and privacy. We can finally have both. And that brings me to the final question I want to leave you with. As we continue this journey, moving from securing data to securing computation, what will a provably correct and deeply private digital world actually look like?